Hello children. In the last video, we have given a very brief introduction about the chapter magnetism and matter. In this video, we are going to see the properties of magnets in detail. So before going into that properties, let me explain what this magnetism is. Now, a substance that attracts piece of iron and steel is called a magnet. And this property of the substance is called magnetism. In nature, a typical black stone is found which has the property of attracting tiny iron particles. For example, iron oxide. Iron oxide is that kind of substance. And such kind of naturally obtained materials which can attract tiny iron particles are called as natural magnets. But we have got artificial magnets also. What are those artificial magnets? Whenever we pass electric current through a wire wound over a magnetic material like iron or steel, that wire wound material behaves like a magnet. That kind of materials or structure is called as artificial magnet. And what is the advantage of artificial magnet over natural magnet? The main advantage is we can have a desired strength and shape for this kind of magnets. For natural magnets, we cannot manipulate the strength of the magnet or the shape of the magnet. But in artificial magnets, we can manipulate the strength and shape of such magnets. Now, you might have seen different kinds of magnets. For example, you might have seen bar magnet, you might have seen horseshoe magnet, you might have seen magnetic needles. This kind of magnets you might have already seen. Here we are going to explain all the properties associated with magnets with the help of bar magnet. And how does a bar magnet look like? You could see that in your screen. Right? Now we are going to explain the properties associated with this particular bar magnet. Now, the attractive property of a magnet is basically concentrated in two regions near its ends. This is the first region and this is the second region. So, the attractive property of the magnet is concentrated near to its ends, and these regions are called as poles of the magnet. So, this is the first pole and this is the second pole. And these two poles are called as North Pole and South Pole. Now, how do you basically identify this North Pole and South Pole? What you have to do is, you have to freely suspend this magnet. Take a thin piece of string and hang this magnet with the help of that string. Whatever is our geographic North Pole, in that geographic North Pole, the North Pole of the magnet will align itself. And whatever is the geographic South Pole of the Earth, in that geographic South Pole, this South Pole of the magnet will align. So what I can say is, a freely suspended magnet can align itself in the geographic North Pole and South Pole. And by that means I can identify which is my North Pole and which is my South Pole. So remember this particular point, attractive property of the magnet is concentrated at its ends and you call that as poles. For a magnet you have got two kinds of poles. In one extreme end I can consider one pole, that is your North Pole, and in the other extreme end I can consider the second pole, which is called as South Pole of the magnet. Hope this point is clear to you. Now let's move on to the next point. Now we are going to discuss about magnetic dipole. Now before going to explain magnetic dipole, let me remind you of electric dipole. What is electric dipole? Electric dipole was nothing but equal and opposite charges separated by a distance, right? A very small distance. I will draw it here. You have equal and opposite charges separated by a very small distance 2a. This was called as your electric dipole. Similar to it, we have got magnetic dipole. But instead of charges, I will be having poles. So if I consider a bar magnet which is represented here, it has got two poles, the north pole and south pole. This is a south pole and north pole. The function of charges in electric dipole, whatever function is done by the charges in electric dipole, same kind of function is done by the poles in your magnetic dipole. Okay, and these two poles are separated by a distance 2l. Separated by a distance 2l, and this distance is called as magnetic length. Magnetic length, the length of the magnet. Okay, but don't get confused with geometric length. What is the geometric length? You might have seen your bar magnets. You take a scale and you measure the length of that bar magnet. Whatever length you are able to observe there, that length is called as geometric length. And this geometric length is not equal to magnetic length. Okay, magnetic length is the distance between the north pole and south pole of the magnet. Geometric length is the distance between the two extreme ends of the bar magnet. And remember, your magnetic length is always less than geometric length. Now if you want to have a specific value there, you can copy it down, but this is not necessary as far as you are concerned. Your magnetic length will be equal to 6/7 times geometric length. So you could see that your magnetic length is less than that of your geometric length, but we will be concentrating more on magnetic length only. We won't be concentrating on the geometric length. Okay, so the distance between the two poles are known as magnetic lengths. A system of equal and opposite poles separated by a distance is called as magnetic dipole. And remember, whatever magnetic length you are measuring here, that magnetic length is a vector quantity. Okay, magnetic length is a vector quantity. And what is the direction of this magnetic length? The direction of magnetic length is always assigned from south pole to north pole. This is the direction of your magnetic length. Just like you define a direction for dipole moment, which is from minus q to plus q, I can define a direction for your magnetic length, which is from south pole to north pole. Okay, now the pole strength is represented by the letter Qm. Now you know that Q is the representation of charge. Okay, charge, electric charge. Now Qm represents magnetic charge. Qm represents magnetic charge. So what function your electric charge does in electrostatic, same function the Qm, the pole strength, does in your magnetic properties. Okay, same function does in your magnetic properties. And always remember, there is nothing called as magnetic charge. It's a hypothetical concept. To compare these properties with electrical properties, we are defining a kind of charge called as magnetic charge, which is a hypothetical concept. Okay, so Qm represents the pole strength of the magnet. Okay, and the SI unit of pole strength is ampere meter. SI unit is ampere meter. SI unit of pole strength is ampere meter. How we are getting this ampere meter, we'll discuss in the upcoming videos. Okay, so the distance between the two poles of the magnet is called as magnetic length. The direction of the magnetic length is assigned from south pole to north pole. The representation for pole strength is Q subscript M. It's not Q into M, it's Q subscript M. Hope you understood this term also. Now let's move on to the next slide. Now we have discussed about electric dipole moment, which was the product of magnitude of any one of the charge to its distance between the charges. Similar to electric dipole and electric dipole moment, I can explain the properties associated with the dipole, magnetic dipole, with the help of a property called as magnetic dipole moment. The electric dipole properties were explained with the help of electric dipole moment. The magnetic properties associated with the magnet will be explained with the help of a magnetic dipole moment. Okay, now magnetic dipole moment is defined as the product of any one of the pole strength to its magnetic length. Okay, so pole strength multiplied by magnetic length is called as magnetic moment. Magnetic moment, or I can say magnetic dipole moment. Okay, since your dipole length is a vector quantity, your magnetic moment is also a vector quantity, and the magnetic moment will be assigned a direction from south pole to north pole in the case of a bar magnet. So if I draw a bar magnet here, where this part represents north pole and this part represents south pole, the length, magnetic length is provided. We are providing a length for the magnetic length from south pole to north pole. Similarly, the magnetic moment will also be having the same direction as that of magnetic length. So the direction of magnetic moment associated with the bar magnet is from south pole to north pole. Don't get confused with the magnetic dipole moment in the case of a current carrying loop. In the case of a current carrying loop, that magnetic moment was defined as current into area. Now when you deal with a magnet, you don't have a current there. So you are not supposed to use the concept of current into area in the case of a bar magnet. So whenever you are asked to find out the magnetic moment associated with the bar magnet, you have to use this expression. Any one of the pole, the strength of any one of the poles multiplied by the length of the magnetic length of the bar magnet. Okay, so if you have studied the electric dipole concept, it is easy for you to study the magnetic dipole concept also. Similar kind of explanation we are providing. The only difference is one is electric, the other one is magnetic. Okay, so remember this particular term, magnetic dipole moment. All the properties associated with the magnet will be explained in terms of magnetic dipole moment. Okay, now let's move on to the next slide. These are some of the important properties that you have to remember. Magnetic monopoles does not exist. What do you mean by magnetic monopoles? For example, if I consider a bar magnet, any bar magnet will be having north pole and south pole. Now if you cut this bar magnet splits into two pieces, and it cannot exist like this. It cannot exist like this. That is, it cannot exist with only north pole and south pole alone. Isolated north poles and south poles cannot be observed in the case of bar magnets. Whenever you cut it, what automatically happens is each piece becomes a magnet. Each piece becomes a magnet. Okay, each piece will be having this north pole and south pole. Each piece will be having this north pole and south pole. Clear? So monopoles doesn't exist. That means in magnets you cannot see isolated north poles or isolated south poles. This is one important difference between electric charges and magnets. In electric charges, isolated charges can exist, right? A negative charge, an isolated negative charge can exist in space, an isolated positive charge can exist in space. But in the case of magnets, this north pole, isolated north pole or south pole cannot exist. They exist as dipoles itself. Every magnet will be having north pole and south pole. So whenever a bar magnet is cut into two parts, we get two magnets. This point also you try to remember. Another important point you have to remember is whenever you are going to cut a magnet into two equal parts along its length. Along its length means along its axis. Suppose if this is my bar magnet, this is my bar magnet, my pole strength will be provided here. Okay, now if I am going to cut this magnet along its axis like this, such that it split into two halves, then what happens is the pole strength, whatever pole strength you had here, that pole strength will be divided into two. for each piece of magnet, you will be having a pole strength half the pole strength of the previous magnet. So when pole strength reduces, automatically our magnetic moment also reduces. Why? Because magnetic moment is nothing but the pole strength multiplied by length of the magnet. So whenever the pole strength reduces, the magnetic moment will reduce. This happens when you are cutting this magnet along its length, or I can say along its axis. Now another important property you have to remember is, suppose you have a bar magnet like this and you are cutting it perpendicular to the axis. If this is the axis of the bar magnet, if you are cutting it like this, making it into two pieces, what basically happens is the pole strength remains the same, your QM value remains the same, there is no change, but your magnetic moment reduces to half. Why? Because when you cut this into two equal halves, the length gets reduced. So this becomes L, this becomes L. So if the length gets reduced by half, then automatically the magnetic moment also gets reduced into half. So remember those two important points. You can expect concept based question from this section. Whenever a magnet is cut into two equal halves along its length, its pole strength reduces to half and its magnetic moment also reduces to half. Whenever a bar magnet is cut into two equal halves perpendicular to its length, its pole strength remains the same, but its magnetic moment reduces to half. Okay, now hope you understood what a magnetic dipole is, a magnetic dipole moment, and what are the important properties associated with this particular bar magnet. Now in the next video, we'll discuss the value of magnetic field along the axial line and the equatorial line of such magnetic dipole. We won't be deriving it, we'll just explain, we'll compare the results with electric dipoles, and we can easily manipulate, we can easily form the magnetic field expressions